And so, yeah, thanks everyone for attending. I mean, our national lab team is really excited to get going on this program with our goal to be able to identify and characterize these undocumented orphan wells, and also working with all of you because it's clear that these different entities have already done a lot of good work in this area, and we certainly don't want to reinvent the wheel. And so I'll quickly set up what we're trying to accomplish in these technical sessions. We've put together 4 20-minute technical talks with good time for questions. So, please chime in the chat. And so the topics we're going to describe are, the need for research in this area to be able to identify and characterize these wells. And then what are the technology ideas, to improve the current state of the art? And that could include everything from low tech to high tech. And then finally, what do we want to what do we want the outcome to be for this program? And I want to say that we're just in the planning phase for this, and we're gathering information, and we want information from all of you. So first, thanks to the IOGCC, who put together this really nice survey with us, with the states, to get their input on, undocumented orphan wells, and we've received input from 30 states already. Uh, uh, and it's really pretty eye-opening to know, because it really helps us guide us where we want to go. And we want to emphasize that this is an ongoing discussion for us, because our goal is to certainly not develop a bunch of technologies in a vacuum. We want to be able to develop it so that you can actually use it, which means it has to be practical, economical, has to improve what you're already doing. And that requires more than this workshop, but an ongoing discussion. And part of this program, we want to be able to test these ideas out in the field over the course of this program. So that's going to require a lot of interaction with you as well. And so we're going to start out with Natalie Peckney of NETL. Previous speaker actually talked about some of this NETL work, and she's going to describe, the need for this research to be able to do a better job in identifying and characterizing these wells. And so I'll turn it over to you, Natalie.
Thank you, Hari. Okay, so I'm going to be giving some background information that kind of helps put the problem of undocumented orphan wells in context. And then I'll describe some of the current state of the science with respect to finding and characterizing these wells. So let's start with a little bit of history. Kurt already mentioned that the first commercial oil well in the U.S. was drilled by Colonel Drake in Titusville, Pennsylvania in 1859. And you can see him there in the photo with the top hat. He's standing in front of an engine house in Derrick. So very quickly after that, oil boom progressed in this area in Pennsylvania and then spread to other regions of the United States. So this historical photo on the right from 1865 kind of helps put the scale of the abandoned wells problem in perspective. You can just see the proliferation of oil derricks across the hillside. And for the first several decades of the oil and gas industry, regulatory actions were really not on pace with development, and so there's a lack of detailed, accurate documentation and site reclamation, so that's resulted in this environmental legacy that's left for us to manage today. You've already seen this graph. Tim Reinhart showed it earlier, but just looking at the magnitude of the mitigation effort, it's difficult to estimate because there's so much uncertainty about just how many orphan wells exist in the United States. So in the bar chart, you see the number of documented orphan wells by state. It's from the IOGCC 2021 report. And of the 32 states reporting, Pennsylvania, Ohio, Oklahoma, and Kentucky are the top 4 states with numbers in the tens of thousands. And the total number of documented orphan wells, again, is about 130,000. However, estimates of undocumented wells make the total population much higher. And again, you've seen this number, but the IOGCC estimates between 310 and 800,000 undocumented orphan wells in the U.S. The EPA, however, estimates quite a significantly larger number at 1.1 million undocumented wells. And their estimate is based off of the NVERIS data set. This is formerly Drilling Info from the 2020 greenhouse gas inventory. The EPA reported that the U.S. population of abandoned wells is about 3.5 million, with 2.9 million of those being oil wells and 6.6 million being gas wells. So the EPA's methodology is to compare counts from historical records and USGS data with the number of abandoned wells in the NVERIS data set. And that's how they come up with the estimate of 1.15 undocumented abandoned wells. So there's discrepancies between the NVERIS database and the state agency databases, and clearly the number of undocumented orphan wells is highly uncertain. So if we try to put the methane emissions from orphan wells into context, we can look at what the EPA has done, because they're estimating emissions from documented and undocumented wells using what they consider the best available information. The EPA began including abandoned oil and gas wells in the annual greenhouse gas inventory in 2018. And one challenge was to just simply define the emissions category. And this was already mentioned, but states might have different well status terms and definitions. So the EPA settled on defining abandoned wells as wells with no recent production and not plugged, wells with no recent production and no responsible operator, or wells that have been plugged. And they estimate emissions by calculating an emissions factor, or mass of methane emitted per well, by an activity level, or number of wells. So the pie chart shows that abandoned oil and gas wells, which is the yellow slice, contribute about 3% of total methane emissions from the energy sector. So it's not a large contribution. However, there's significant uncertainty in both the emissions factors and the activity levels that were used to make this estimate. To go into a little more detail, this map shows the data sources for the emissions factor estimates, where the emissions measurements were made and how big the sample sizes were. The coverage across the United States, as you can see, is not great. There are a lot of areas that aren't represented at all. And sample sizes, if you look at the number of wells sampled, they're in the tens of wells or less for each area. So there have been other studies done since the three referenced here, including some done by NETL. But so overall, there's evidence that more data are definitely needed to characterize orphan wells with respect to their methane emissions. We want to look at measurements collected in other U.S. regions, assess the temporal variability, and also compare emissions to various parameters that might reveal relationships that would allow us to have predictive capability, like are there factors that indicate whether a well might be leaking and what kind of quantity might be expected. And this is something for which currently we don't have enough data. And I did see a question in the Q&A about this, and I would say that parameters like well age, surface equipment type and condition, location, well depth, et cetera, the only parameter to date that we've seen a significant relationship is geographical location, where wells sampled in the Appalachian Basin seem to have higher emission factors than those sampled elsewhere. But that's really the only statistically significant relationship that we've seen so far. Here are the tables from the greenhouse gas inventory that show the emissions factors. So based on the available data, the EPA decided to use two sets of emissions factors, one for plugged and unplugged wells in the Appalachian Basin and another for wells in the rest of the U.S. So if you look at the emissions factors, I know there's kind of hard to see in the table, but plugging wells definitely has a positive effect on curbing methane emissions, as you might expect. The average emission rate for unplugged wells is 5,000 times more than that for plugged wells. We look at some data collected by NETL. We looked at methane emissions measurements for hundreds of orphan wells, both plugged and unplugged in several U.S. regions. And this first slide shows unplugged wells. And as is typical for oil and gas sources, the distribution of emissions is what we call fat-tailed. So many of the wells emit no or very small amounts of methane, but a few in the population emit much higher amounts. So these are what we call the super emitters. And this data for unplugged wells shown here for areas in Pennsylvania, Kentucky, and Oklahoma, all exhibit this fat-tailed distribution. We don't have as much data for plugged wells. Of about the 90 plugged wells that we've sampled, only one was actually leaking. However, its leak rate was pretty high. So that one leaking measurement greatly skewed the average emission rate. So that's the challenge with using average emission rates for sources that have fat-tailed distributions like this. Finding or just not finding those super emitters can have a big impact on average emission rates or assumptions you make about the population. So with respect to characterizing methane emissions, clearly more research is needed to conduct representative sampling across the entire United States and for different well types. But being able to even find the undocumented wells is, of course, a major challenge. So in terms of state of the art, one proven technique is to conduct aerial magnetic surveys. Because a well with magnetic casing, with metallic casing is oriented vertically and it's perpendicular to the Earth's magnetic field, the magnetic signal detected at the surface shows a monopole anomaly. So if you survey a large area in a grid pattern and map the magnetic signal, these anomalies show up pretty clearly in a heat map like the one shown on the right. This was Salt Creek oil field in Wyoming. It has more than 5,000 wells and it's about 40 square miles. So back in 2005, when NETL surveyed this area with a manned helicopter, the cost was about $230,000. Nowadays, we can do these surveys with drones, which does reduce the cost. So this aerial magnetic surveying technique provides quick and broad regional coverage. High sensitivity of the magnetometers that we have today yields a high success rate. We've proven at one particular field location where we were able to verify, we found 93% of the wells, so that's a pretty good success rate. And we can even find wells that have been buried. In one location, we estimate that we were able to find wells that were over 100 feet deep. However, this approach can be expensive because it requires skilled aircraft operators and data analysis. Using a drone does cut down on the cost, but there are limitations then because the drone has to remain within line of sight, and usually they're battery powered, so the range is reduced compared to a manned helicopter. Another aerial surveying technique that's being used is using LiDAR. Being able to map ground surfaces can reveal features in the land that are characteristic of well pads. So if you look at this sketch on the right, it shows typical well construction, where you have the rectangular engine house with a derrick on the one end. So in the middle figure, you can see these bench-like well pad features cut into a hillside. This is actually in Oil Creek State Park in Pennsylvania. We were able to georeference the historical photo I showed on the first slide and again here, and we could actually pinpoint the location of those derricks shown in the photo with actual locations on that hillside. So sometimes historical data like photographs can provide helpful information about well counts and location. LiDAR surveying has similar advantages to magnetic surveying in that you can get broad and quick regional coverage. And there's the same consideration for cost versus coverage with manned versus unmanned aircraft. And also, if states already have LiDAR data, it might not currently have the sensitivity that's required to be able to find these features. But sometimes you can look at the raw data and reprocess it such that you can improve the imaging. However, this is important, LiDAR is only successful if the ground has remained relatively undisturbed since the well was abandoned. So no farming or other land clearing activities. Also, it requires GIS expert to process the data. Like for instance, when we've done this, you have to filter out false positives caused by fallen trees, because when the tree falls, it creates a long vertical shape by the trunk and a big depression in the ground from the root ball. So there is some data processing involved there. It's not always very easy to do. We can increase use and improve upon the efficiency of well finding techniques. And we can certainly collect more information about methane emissions, but there are certainly other well hazards that require characterization, such that informed decisions about well plugging can be made. So these next couple slides that I'm going to show have well hazards that have been shared with us by New York and Pennsylvania, by those agencies, so thank you to them. If I've missed any hazards that other states are interested in, we'd certainly like to hear about them. So proximal hazards are considered for both human and ecological receptors. Like, is a well near a building, near water supplies? Is it on agricultural land, like the pasture shown in that first photo there? Is it near wetlands or in or near waterways, like shown in the other photos? Or is it in an area with endangered, threatened, or protected plant or animal species? Is the well leaking? Is there oil contamination, like the picture on the right? Has methane been detected? You can see the infrared photo there. If I were able to play the video, you'd be able to see the methane leaking out of the well. Or is hydrogen sulfide or radioactive material present? Norm. Are there well integrity issues or physical hazards? We've seen some wells that we heard were called man-eaters. So basically just a big hole in the ground, likely unstable ground. It's pretty dangerous. And doesn't look very impressive, but that picture on the top is a man-eater. When you get up close to it, you can see that you could in fact fall in there. And specific to states with coal mining is the well in the vicinity of an underground coal mine. Usually these hazards can be identified fairly simply with a visual inspection, but the methane emissions measurement can be a little more challenging. Firstly, there's a variety of well configurations, so different infrastructure that's been left behind, ranging from just a hole in the ground or casing cut off near the ground surface, like the pictures on the left, all the way to having an intact wellhead there, to a wellhead still connected to pipes and pump jacks and other equipment. So the approach taken to measure the emissions can depend on the configuration of the well, and one technique might not work at all well configurations. And also, it depends on the need to have either a more qualitative assessment versus a quantitative measurement. So if you just want to know, is the well leaking or not, a more simplified approach might be better. But if you need to know an actual emission rate, it can get a little more time-consuming or expensive. So these various emissions measurement approaches can be evaluated based on cost, the time it takes to take the measurement, the accuracy and limit of detection, how easy it is to use, and is it field portable, what kind of skill level or training is required to take the measurement, and is it effective for any or many different well types. So there are certainly other approaches out there and many qualitative approaches, but in the published literature for quantitative approaches, there are two main sampling techniques: high flow sampling and flux chambers. So high flow sampling utilizes a high flow rate to pull a vacuum that includes the leak. It captures the whole leak as well as background air. So after you do a background correction, the methane flow rate from the leak location is given. So I'm not endorsing any particular instrument or model, but the backpack unit that you see in those left couple of photos has several different attachments on the end of the hose so that you can adapt the measurement to fit the well configuration. So these high flow samplers generally cost in the neighborhood of maybe $40,000. It's a pretty quick process, probably takes less than 30 minutes per well to take the measurement. You get a reasonably good limit of detection. They're very field portable and they're easy to use, and they're effective for many different well types due to those attachments. But this is a snapshot type measurement, just giving you the emission rate at that moment in time. So it doesn't tell you anything about temporal variability unless you go back and take repeat measurements. And it also is not effective if the well has been buried. Flux chambers, on the other hand, so these typically involve the use of a rigid chamber placed over top of the well, and they can be static with no airflow, or dynamic, which it has constant known flow rate through the chamber. So a dynamic flux chamber, those are shown in the middle in the right photos. And the one on the right actually shows a network of small flux chambers. So the chambers themselves can be relatively inexpensive, but the overall cost of the flux chamber monitoring really depends on the price of the methane analyzer, and those can get pretty expensive. But this approach has, you can get really low limits of detection. You can account for temporal variability if you do the measurement over enough time. However, you might have to custom build the chamber and test it, which can be very time consuming. It has to fit over the well, so depending on what's there, building and testing that chamber can be complicated. And it's not super field portable if you're doing the dynamic flux chambers, because you have to have this gas cylinder and take it out in the field. It's more like a semi-permanent type of installation, so it's not easily moving from well to well to collect the measurement. And it does require some post-processing of the data to calculate the emission rate. So this is just a little bit about kind of the current state of the art with respect to how methane emissions measurements are collected. So this has already been touched on a little bit, but the states that have active well plugging programs have some financial resources for plugging wells, but it's not enough. According to a 2021 study, the median cost of plugging and reclaiming a well is $76,000, but there's a wide variety of costs depending on the well's age, location, depth, and other factors that could make the plugging operations more or less expensive. So the cost of plugging all of the 130,000 documented orphaned wells could range from 2.6 to nearly $19 billion. And that's just for the documented wells. So if you remember, estimates of undocumented wells range from hundreds of thousands upwards to slightly over 1 million. And the bill is providing $4.7 billion to states for plugging and reclaiming orphaned wells. But there's also some nonprofit organizations working to locate, document, and plug wells. However, all this investment is just not going to be enough to plug all the wells in the country. So it's kind of obvious we need to prioritize which wells to plug. If we have good strategies for prioritizing which wells to plug with the resources that are available, we can maximize the reductions in methane emissions and other hazards. So the RDD&D that this multi-lab group is proposing to do will, in part, provide effective means to locate and characterize undocumented wells. And I've thrown in here that the effort will also improve documented well data. I want to stress that just because we have documentation for these so-called documented wells, we've seen that frequently they're not sufficiently detailed. And we've also seen lots of inaccuracies when we go out in the field and using the documented information. Like even if you have coordinates for a well in a state database and you go out in the field and try to find that well, you might not be successful. Or you might find that the well status doesn't match what's in the database, et cetera. So we probably potentially could also be improving documented well data. Strategies need to be developed to target high priority wells for plugging in a way that maximizes impact. And because well plugging is not necessarily designed to be a forever solution, and also because a well might not be a high priority for plugging now, but situation might change somehow to make it high priority later, I'll mention the need for tools and technologies for continued future assessments and monitoring. So this multi-lab research effort is focusing on developing new tools, technologies, and processes for robust, efficient identification and characterization of undocumented orphan wells. Our research technologies, after discussion within the group, we've categorized them into 5 different areas: methane detection and quantification, magnetics and electromagnetics, sensor fusion and data with machine learning, characterization, and integration in real-time practices. So you'll be hearing more about these research areas in the next couple of technical presentations after the break. But until then, this concludes my part of the technical session, and I'd be happy to take any questions.
Okay, thanks so much, Natalie.
Hari, can we just let everybody know that we're taking questions through the Q&A. You must type your questions in. We're not answering raised hands and what have you. So please type your question. Thank you.
Got it. Yeah, so we've got a we'll do a couple of questions here and then maybe take the break since everyone needs that and we want to get on schedule. And so one question, Natalie, is for legacy wells, how much understanding do we have on the relationship between well characteristics such as well age, surface equipment type, condition, location, and well depth, and the quantity of methane leakage?
Well, the first most obvious one would be, is the well plugged or not? So, obviously plugged wells have much less methane leakage. But aside from that, the data in the published literature to date just aren't enough to really establish any clear statistically significant relationship, other than, and I did mention this briefly, other than the fact that we do see some differences regionally. So the Appalachian Basin, average emission rates there tend to be a little higher than for other locations in the U.S. And we collected some data for Oklahoma recently. So comparing our data for Pennsylvania, Oklahoma, others' data from states out west, Utah, Colorado, Wyoming. Seems like the three western states were the lowest, Oklahoma somewhere in the middle, Pennsylvania the highest. So could be some regional differences there. But again, if you remember on the map that I showed early in my presentation, sample size across the board is generally pretty small, and there's just not enough information to get real statistical power to see if these relationships exist.
Great, thanks. And so that's the main. Does anyone else, if you want to quickly type something in, I guess if I could ask one question for Alicia, who's also a panelist, just for the USGS. If you're there, how will the orphaned well emission measurements be collected? Will these data be gathered in collaboration with state agencies, or do USGS researchers plan to take field measurements? Has the work focused on understanding factors that influence well leakage? Has that already begun? And if Alicia's not there, we can
Yeah,
tape.
I'm here. I can
Okay.
take that. Yeah,
Okay.
so I think that there's probably two components here that are maybe getting conflated. But so as a part of the kind of overall DOI program and the congressional report reporting on methane emissions, that is all being done under a kind of an interagency working group. So the kind of plan for taking those measurements and how to take them and how to report is being done the USGS, of course, is involved, but that's being done under this interagency group. The project that I highlighted is really just kicking off. That's working to just better understand the linkages between the geologic factors and methane emissions. So I would say TBD on those as we're just still kicking those off. So two different things, but both looking at methane emissions.
Okay, thanks. And so I think we'll take two final questions for Natalie, and then we'll get us back on schedule. So, Natalie, is there research related to looking at a leaking reservoir? In other words, if you don't plug all the wells, won't the emissions end up increasing in the wells that aren't plugged?
Oh, that's a great question. And do we know if there's communication between wells in the same formation? I don't have really any data to back up any claims here, but I will say kind of anecdotally, we were working with a company that was monitoring, doing continuous monitoring at abandoned wells, and we were looking for new sensor technology that would easily allow continuous monitoring, which is kind of tricky because you need to have a source of power, some sort of way of logging the data, and you have to have good enough, sensor detection limits, et cetera. There's a lot of sensors that measure methane concentration, but not methane flow rate, which is what we're after. So that's, a whole nother discussion about sensor technology. But this company was finding that when they monitored emissions from an unplugged orphan well on their property that was in the vicinity of a Marcellus shale well, a deep horizontal well, while they were fracking that well and during flowback, et cetera, I don't know, they could see changes in the emission rate from the abandoned well that they were measuring. So it does seem like, other subsurface activities in the vicinity of an orphan well can definitely cause something to happen, migration of fluids. So it kind of further emphasizes the point that I made earlier, that just because a well is not plugged currently and it's maybe not high on the plugging priority list, should other things happen like nearby subsurface development, it could push that well into a more higher risk or higher priority for plugging.
Okay, thanks. So I think in the interest of time, let's go ahead and take a break. We are taking everybody's questions down, so the ones we don't get to, we will, answer offline. And so thanks,
Um,
Natalie. Excellent talk.
we are just a little bit behind, so it's going to be 1 p.m. for the break, so we'll start back up at 1:15. Fair enough?
Sounds good.
Yeah, and you don't have to log out or anything, just head off to go get a snack or go to the bathroom or what have you. Thank you. Hey, everyone, we'll be starting back in about 5 minutes. Hello?
We're here, Amy.
Yeah, we're here.
Caitlin?
Yes.
Shall we get going?
Yes, Hari, we're ready to go when you are.
Okay, great. Well, welcome back, everyone. So our next talk is going to be by Brian Will, Lawrence Livermore National Labs, and he's going to be talking about some of the well finding technologies that we're thinking about for undocumented orphan wells. So thanks, Brian.
Yeah, thank you. So everyone, yeah, my name is Brian Weil. Just a quick background on me. So I lead the autonomous sensors program within our energy program in our global security directorate at the lab. Admittedly, don't have a huge background in well detection, but have a really strong background in developing these technologies. So excited and thankful to have this opportunity to talk with you all today. Quickly, what we're going to go over, motivation, I'll touch on that briefly, the challenges specifically with identification, and then start to dive into some of these technologies, especially sensing technologies is what I'll focus on. But then I also want to talk about sensor suitability, because there's been a lot of talk today in general about really making sure that we're addressing the problems and how the technology, we're not just going to throw new sensors at it, but really put together a meaningful framework and a meaningful system that will address the needs and the many different needs that were discussed today. And then of course, circling that back to, you know, what does this mean? What is our success and what are we trying to really do here? So I won't go into the high level motivation. I think that's been covered pretty well and better by other people earlier today, and probably ones that we'll talk later as well. But what I do want to distinguish is the motivation in determining the difference between identification and characterization. So when you make these two distinct different problems, it allows you to really focus on one and then the other, and then really you know, attack them with the right technology for each level. And the hope here is that you can kind of create a hierarchical approach in that your technology will meet the needs and address the specific issues with identification versus characterization. Now with identification, you know, there's kind of three key areas I think are challenges. And again, in a lot of the pictures you guys have seen today, and those of you who know wells better than I, you know, you already know this, but basically the well is not uniform in any way. When we're talking about above the ground or below the ground, depending on what time it was put in, the geographical area and the demands of a well in those areas, and the techniques for pumping, it's all going to be very different. So now we have something that, you know, we need technology where you can basically key off many different features. And that isn't just true of above the ground, it's also true of below the ground. So depending on the casing material, the depth, the size of the well, different technologies are going to be better suited for those kind of wells. So again, we have a problem set where we're trying to detect something that has high variation. In addition to that, as far as you know, applying technology to these areas, there's very challenging and very varying environments. Whether it's in an open area, in a forest, on a hillside, is it visually occluded, you know, by trees? Is it underground and there's not very much above it? And when you start to even apply technologies that try to see more into the ground, you have to worry about things like soil type, and you know, what's really below there around the well. So again, high variation, not just in the objects we're trying to detect, but in the environments we're trying to operate in. And then of course, that third tier is that this is really a wide area search problem. These are prevalent across the nation. We've had people discuss earlier how, you know, we believe that they will be all in similar areas, but of course you want to verify that and you really want to know that, and you do still need technology that can apply to a wide area and can scale nicely. Obviously doing everything by foot or by person does not scale well. It's gonna become very expensive when you're trying to touch wide areas. So this technology really needs to be able to scale nicely and in its nature be able to be applied to wide areas. So this is a quick overview of some of the technology that I'll talk about. One thing to keep in mind, this is not by any means an exhaustive or a deep dive in any of these technologies. And certainly there's other technologies that can be used. And again, when you talk about this hierarchical approach, there's other ideas that fit into this. For instance, something I believe that will be touched on in a later talk is the idea of using technology to analyze historical data, using machine learning techniques and natural language processing to go through past documents, past data, and try to piece together and understand maybe where wells will be, so that again you can cue technology later on to go look in that specific area and reduce that wide area search problem. But what I'm going to talk about mostly here is really the sensing technologies and ways in which to more directly detect those wells or the feature of the wells as they exist. Other things to keep in mind is, you know, again, this is not a single sensor approach. We know we will want to apply multiple sensors, and in that have sensor fusion, so that we can really, you know, take advantage of all the different sensing techniques and really have something that's greater than the sum of its parts. So applying cutting edge machine learning techniques using signal processing to make sure we're not just throwing blind data at the problem, but actually understanding what the data means, turning it into a useful data product before we're shipping it off into a detection algorithm. And then the last tier is vehicle integration. So we've heard a lot about today. It's certainly the trend in industry is to push technology onto small unmanned aerial systems. There's been many industries where they've seen that it greatly reduces cost and increases effectiveness. We strongly believe in that as well. But of course, that does not count out, again, because of the high variation with what we're trying to do here, that manned aircraft, unmanned ground vehicles, and also handheld and wearables for boots on the ground is still very applicable, making sure we have technology that can fit into all those different concepts of operations. So one of the first technologies I'd like to talk about is pretty simple in nature, but it's a stereo camera approach. So really what you have is two cameras with a fixed geometry. And what you can do there is create not only optical imagery, so this is your typical kind of red, green, blue images, but you're also able to create depth images similar to what a LiDAR does. But again, what you have here is a very simple, very cheap, very effective sensor that really gives you two features, depth and color imagery. And what you can do, just like a LiDAR and what was shown before in the previous talk, is that you can really understand surface features and structures. So you can use traditional object type detections. You can train up machine learning techniques to try to pick out certain features of a well, say it's the wellhead, say it's an engine house, or any of those other structures that are associated with wells. And you can not only do that on optical imagery, but you can also do that on depth imagery. These systems are much lighter, much more cost effective than LiDAR. The biggest drawback would be that their standoff, or how far away you can detect, is usually not as great. However, their resolution can rival or even surpass LiDAR. So as mentioned before, some LiDARs, especially older LiDARs, didn't give you great depth resolution. We've experimented a lot with depth cameras, and we've even proved that you can detect footprints in relatively hard soil from a UAS. So these give you incredibly great resolution and really give you a great basic data set where you can start applying just standard algorithms and start doing automated detections of wells. Moving on to another one, a lot of people who have done remote sensing may be familiar with this, certainly from even space remote sensing, but hyperspectral imagery. This is basically a much more advanced optical camera. Instead of traditionally getting your response off of a surface in red, green, and blue, you're going to get it across a much wider and much more high resolution spectrum range. So what the advantages here are, you can not only look at surface features from their red, green, and blue component like we traditionally do, but you can start to get spectral responses and categorize materials. And of course, as you push either into the UV or into the infrared area, that's where things get really interesting. So this has the possibility of doing gas detection, not just methane, but other gases as well, from a relatively high standoff. So again, on unmanned systems. But it also gives you the ability, and as the technology gets more mature, and these are already systems that can be placed on systems and out in the field, is that it's going to be able to really give you a really great feature set in which you can apply, again, some of the cutting edge machine learning techniques to really pick up what's on the surface and detect possible leakage already, groundwater, and then again, any growth or anything that's associated with a well that you would now be able to pick up and detect. These are relatively expensive, a little more heavier weight, but again, both in the commercial sector, but also where a lot of different labs, many labs on this workshop have been pushing, is to reducing the size and weight and cost of these hyperspectral imaging sensors. So much so that traditional infrared sensors that would normally be much larger and heavier and have to be in unmanned aircraft, or sorry, in traditional manned aircraft, can now be pushed to unmanned aircraft. Magnetometers, so they've been discussed already. However, there's actually been a trend to really increase the capability of this technology in the last few years. So one push is not just doing a simple magnetometer, but doing a gradiometer, in which case you are actually putting multiple magnetometers in a certain geometry, and there's a lot of studies on which ones are best, especially depending on polarizations. And that can certainly be a study that could be done to figure out what the best configuration for well detection is. But again, the sensitivity is being increased, the weight's being reduced, and with the use of gradiometry, you can actually apply newer cutting edge algorithms that really, really increases the sensitivity of your sensor, where now you can again increase the standoff of operating the sensor from where you're trying to detect, but also has the ability to pick up much finer ferrous objects, basically, you know, the size of the thing you're looking for. So this is one where it's already being used. It can definitely be increased, the capability where, you know, where the technology is going today. And again, it can be integrated on, you know, more efficient and easier to use unmanned systems than it probably is currently, again, because that technology is going to allow you to fly at higher altitudes and not have to worry about the environment as much. LiDAR is another one where it's obviously being used today, but where the important factor here is that it's constantly being upgraded and increased in its capability. So the resolution is being pushed. So making sure that we're integrating the latest LiDARs, giving you potentially sub-centimeter resolution and higher scan rates is again gonna make it more feasible. You're gonna be able to increase your standoff, fly your drones higher, fly them on unmanned systems, and get the resolution you need to pick up fine details, again, like what was being shown in the talk before. In addition to that, when you get this higher resolution, your backend algorithms are going to change. So, you know, we want to make sure that we're mating the latest algorithms with the newest technology and making sure that we're taking full advantage of those resolutions. Ground penetrating radar is another very interesting area. We kept this one on. It can be used. Traditionally, a lot of people that may have experience with ground penetrating radar know that it can be somewhat cumbersome and also include a lot of professional or experienced users to be able to understand what the data means, what it looks like, and of course, operate the system. This is actually a big body of work for Lawrence Livermore National Lab as well. We have a system that's much more intuitive. It actually does subsurface imaging, so it creates true 3D reconstructions. But in general, ground penetrating radar is something that could still be used for the identification stage and in that wide area search. And of course, it's an area that's still under great development. There's new ground penetrating radar systems coming up. There's much more approaches of doing imaging techniques and providing machine learning detection abilities so that it doesn't need to have a experienced user to operate it anymore, but it can be pushed to someone who can just literally hit a button and say go. And again, what this is very different from any of the other technologies described before is what you're really looking at here is now subsurface. So you don't have to worry so much about trying to detect you know, secondary or tertiary features of a well, but you can actually try to start detecting the casing, the hole itself, and other features that you will know with great certainty that you're actually seeing a well. So this technology, while a little more cumbersome in its nature right now, can definitely you know, be used now and also in the future to really confidently detect wells. And I think this is something that's been talked about a lot, will be talked a lot in the next talk as well, but gas sensors as well. So, you know, here again, we're just using a simple gas intensity sensor. It can look at the concentrations, not necessarily the flow rate, but something that's very easy to be able to detect those wells that are emitting methane or emitting any other type of gas. These are relatively cheap sensors, so it's one of those cases of why not include it. You can pretty much put it on a UAS or a wearable with any other sensor. It's not going to add much cost or weight to you, and it's going to be able to at least detect those high emitting wells, which obviously is, you know, a huge concern and something that you wouldn't want to not include because it's relatively low hanging fruit in this case. And again, these systems are ready to go. There's actually companies that can even you know, loan out products and you can test today and start kind of sniffing around areas and seeing if you have any emissions going on. So another topic I want to get into is what's really important and what's awesome about this process so far, and I can't say how happy I am to be involved in it, is that you know, we're kind of in the entry phase of really trying to come up with new and exciting technology and also being able to match current existing technology within the labs to this problem set. So, what's almost as important as understand the technology now, but is developing a process in which we will be able to funnel new technology, funnel the developments that the labs are making, and provide that technology to this problem set in the future. There's been talk about this being, 5-year, 8-year program. Obviously, technology is going to mature and grow in that time frame, and we want to make sure we have a process of assessing that technology and understanding how it works with either established technology or other new emerging technologies, so that again we can always put our best foot forward in well identification and characterization. So the first step is, and there's been a lot of talk about it on these on the different talks today, is requirements. So taking these requirements and trickling them all the way down to what that means for a sensor and a system, right? Establishing that, and this is going to be done with strong interaction between the technology developers and the stakeholders. And I mentioned some of them in these sensors today, but going over things like their ability to detect. Are they looking at primary features such as the well structure itself? Are they looking at secondary features such as supporting structures of the engine house? Or are they looking even at tertiary features like, maybe there's potential growth always around a well, or there's some, effect that the old well has on an environment that we can now put sensors forth to detect. We want to know what these sensors' ability are. And then of course you have your more operational requirements of, what kind of standoff can I do? What scan speed am I willing to do? And if we take these different metrics and we start to rate our sensors, we can understand where the gaps are. And again, both the gaps currently, gaps in the future, and as emergent technologies come out. And I know it's a bit of an eye chart, but it's just a point that, we can do this with the technology that's been talked about just today. And we can get an idea of utility for each of these sensors across these metrics. And then what we can do is start to assess, well, what if we combine them? So if we know, detection, having good detections is a certain a utility, having the ability to have high standoff because it makes it much easier to deploy this sensor and use it has a certain utility, making sure this scan is done at a certain speed so that we can cover the area we need to cover. And then, ones down the line, such as, processing, is this data I can get in a day? Is this data I can get in a month, a week? What am I willing to do? And you can start to look at all these technologies and look at the combinations of them and really come up with a system that meets your needs and is giving you the most utility at any given time. And this is important to address, not just, again, in the identification, but characterization in anyone down the line, but also state by state, because these will be different. If you're in a flatter state, your standoff might not be as big of a deal to you because your wells are going to be more accessible. So, it's important to have this process, to understand this process, and to really allow us to drive to technology that ultimately meets your need at a cost-effective way. And as far as success metrics, we want to provide the ability for you to quickly, effectively, both in manpower and cost. I guess cost really, ultimately is the goal here. But to be able to deploy these sensors and start detecting wells, right? Start finding it, or at least at the minimum, start closing that area so it's not such a wide search problem. You can start focusing your assets, focusing your manpower on the areas where a well is going to be. And what we want to do is get our foot in the door, start generating these data sets, start generating these visualizations that scientists can use, other people can use, that can be built upon and used in the future, used with other sensors down the line, and generate those data sets that's going to give ultimately the people that are doing the job what they need to be more effective. And that's pretty much all I have today. I'll definitely open it up for questions.
Okay, thanks, Brian. That was really, really good talk. So we do have some questions. Let me just go through some of them. So what is the resolution that you're able to detect methane emissions from a drone mounted sensors, and how does this compare to airborne mounted sensors that can detect down to 10 milligrams per hour?
Yeah, I can take a quick shot at answering that. I believe the next talk will go into more depth on gas sensors. So we mostly use off-the-shelf ones in the past. I definitely, there's the ones that we use for UAS mounted are much less sensitive. They're looking for relatively large leaks. I don't have a number on that today, but the number that was thrown out there, those sensors would not be able to get down to that low. And it also, again, they're concentration sensors. So they're looking at what is present in the air. They're not necessarily measuring flow. So it will be a factor of the environment that they're operating in as well.
Thanks. Will future magnetometer abilities be expanded to be able to better identify horizontal features such as small pipelines?
Yes, yes. In fact, so with the use of gradiometry, and again, how you do the geometry of the magnetometers within a gradiometer, you are able to pick up, again, a field vector instead of just a field intensity. So with that, and again, taking into the operations of how you move this sensor around, you can actually pick up pretty much any direction, any polarity that exists.
A question about hyperspectral sensors. And so may aerial hyper, maybe, let me see if I can get this. Uh, Aerial hyperspectral survey, would it be a choice as it covers a much wider area, and would it be more economic than ground-based units?
Absolutely. So I know we've done a large body of research in the hyperspectral, and again, we have systems that cover pretty much all the spectrum range. We have ones that focus just in kind of hyperspectral within infrared, which again, when you're talking about gas detection, is big. But we also have ones that cover all the way from near UV to that deeper IR. And in that case, I completely agree. It's very economical. The sensors themselves are expensive, but for your bang for your buck, you're able to fly at a relatively high altitude, scan very quickly. It's very economical when you look at the entire operation.
Do we know approximately at what emission factor methane leaking wells become detectable from aerial platforms from today's sensors?
I don't have an answer for that. Perhaps someone else on the line might have a better answer for that one.
Natalie might.
Yeah, I can jump in. I'll say that the emission factors that we've collected, at the higher end, there's something like, I don't know, maybe like 0.2 kilograms of methane per day. And so if you compare that to the detection limit of some of these aerial techniques, they aren't going to work. But if you get really sensitive techniques, you could be able to detect the super emitters, probably not the low emitting wells, and they're just too small of an emission source to be able to detect at the height that the aircraft would have to fly. Even a drone that could presumably fly at a lower elevation than a manned aircraft, still going to be a really small emission source to try to find. So aerial techniques would probably be just targeted towards finding super emitters and not finding all the wells by their methane signature.
So this is a question that could be for either one of you. I think it's something that's on a lot of people's minds. So prioritizing wells to plug by methane emissions would require measuring methane emissions at a significant proportion of the wells beforehand. And emissions from AOOG wells are too low to detect or measure using aerial surveys, and boots on the ground, would be expensive and time consuming. So given the methane emissions from the vast majority of abandoned wells, does it make sense to spend money to measure prior to plugging?
I would consider using a low-cost, quick and efficient screening technique to just determine if a well is leaking or not. So a more qualitative assessment. You could use, there's a variety of handheld detectors that can look at methane concentration. So then if the well is leaking, then you could go into the more expensive, time-consuming, or complicated emissions measurement approaches. But at least with the screening technology, you're not spending that much time or money, but you're still checking if the well is leaking or not. So if it's not leaking, you don't need to do anything further. Does that make sense?
Yeah. And I got a final question before we move on to the next talk, or actually two more. For well leakage detection, one direct signature we've been talking about is methane concentration and flux. Can we think of other geochemical signatures that could also help us?
Brian, do you want to tackle that one? I'm
I
not really
don't.
aware.
I think that'd be more of a question. Sorry, for someone who knows the different the different gases that come off of a well. Certainly, we would be able to detect them. So again, I'm not sure if the question is so much about would we be able to use them. Certainly, we would. So again, IR hyperspectral is used for detecting more than just methane gases. I think sulfur dioxide or something is common as well. I'm not sure what's in the present of wells, but also we have the ability to fly other gas detectors too. So certainly we could create a system that would use other chemical-based detection methods.
Yeah, and I
Yeah,
think also,
Kurt Klepkowski mentioned, hydrogen sulfide being of interest and other hazardous air pollutants or air toxics. In our research, we've found if you look at the composition of the gas that's leaking out of the well, what we've seen in our data is it's at least 97% methane. So the likelihood of a significant presence of other gases is probably going to be low, but I wouldn't exclude that completely because the sample size that we've collected is still pretty small.
Okay, great. I guess let's wrap this up with one final question for this session. And it might be more Natalie, but we'll see. So do we know a rough ratio between in the wells, whether they have metal or non-metal, non-cased?
I don't have a ratio I could give, or anything at my fingertips that I could quickly look up. But, in our experience, the areas that we've concentrated on, the majority are definitely metal cased. Some of the really, really old wells might have been cased with wood even, but I think those are a lot more rare. There are a lot of incidences where the casing has been pulled. So, maybe a well is left without the casing, at least at the, parts of the well closer to the ground surface. However, like I said, with the finding buried wells via the magnetic surveys, even if the casing has been pulled at the surface and there's still some that remains in the ground, we may still be able to detect that with magnetic surveying techniques.
Yeah,
Right, and I think
that's a good
go
point.
ahead, sorry.
So for magnetometers, I can speak more from the sensor side. We have different magnetometer technology that can detect very, very small amounts of ferrous material. Even cases where there was something relatively large with iron placed, rusted, and we can still detect the remnants of the rust in the ground. So the sensitivity on magnetometers are becoming very high. How you apply them in the environment. So are you flying from a drone, which adds some noise? Are you walking it? That factors in. But the sensors themselves are extremely sensitive to a point where, again, maybe you're not detecting the casing, but if there was ever any type of ferrous material around that well, you may be able to pick it up.
Perfect. So one question came in, which I think is actually a pretty good transition between Brian and Sebastian, who's coming up. And so I think many are kind of curious limits of satellite imaging for orphan wells detection. And, can satellite-based sensors be used for detection of methane superemitters? And I think on top of that, we did have a question before to just clarify. Identify is pretty clear to people. We're trying to find the well, but what do we actually mean by characterization? And that might be a good segue into Sebastian's talk anyway. So that'll be our final.
Can I ask a quick question, Hari? We did have a question in the queue about will contact information be available for some of the speakers in the presentations and things like that they could follow up?
Oh yeah, for sure.
Okay.
Yeah.
Okay. Thank you.
Yeah.
so Ari, yeah, this is Sebastian. So I'm going to take the next talk. Can you hear me okay?
Yeah. So thanks, Brian. Excellent talk. And let's transition with that question for Sebastian's talk.
So do I have the hands to move the slide? Okay, so good morning, good afternoon to the audience. My name is Sebastian Birode. I'm a biogeophysicist at the Lawrence Berkeley National Lab located in California. My work focuses on atmospheric greenhouse gases to support research on the carbon cycle, both from a natural and human perspective, validation of satellite-based observation, and greenhouse gas source attribution. Just as a fun fact, I joined LBNL, the Berkeley lab, when global average atmospheric mixing ratio of CO2 was around 370 ppm. So that'll give you an idea of how far back that was. Today, I'm here to talk to you about the characterization of orphaned undocumented wells after they are found, right? After they are found. So in an ideal world, everything has been identified, and what we want to do now is characterize the wells. So, oops, one too many. It looks like, there is some delays in my moving the slides. Okay. So the outline of my talk is fairly simple. First, I'll give you some motivation as why this task is important. Second, I'll review the obstacles that we face to address these grand challenges. And third, I'll go over some of the state-of-the-art technology that staff at national labs are currently using to characterize well. You've heard a lot about those, but I guess we'll add another layer of mentioning those technologies. Fourth, I'll briefly present the well characterization project team. And finally, I'll conclude on our success metric. Okay, so as we all know, oil and gas wells provide the leakage pathways that connect oil and gas reservoir to groundwater aquifers and to the atmosphere, potentially contributing to water and air quality degradation and anthropogenic greenhouse gases emissions. The latter is important because of the overarching goal of this program, which is to reduce emissions of methane from the oil and gas sector. In order to maximize the impact of this program, well characterization should be done in coordination with state and stakeholder. And I was really happy to hear that there's already a program in place at DOE and at USGS to do this. So I'm looking forward to coordinating these efforts across not only state, but also federal institutions. Quantification of methane from orphan wells will improve also US EPA's estimates of methane emission, as shown by Natalie during the technical session 1. Let's see, next slide. Okay, so what are the challenges that we are facing? So the ecosystems of wells is very diverse across the nation. We will also encounter heterogeneous subsurface and surface condition across oil and gas basin where the undocumented orphan wells are located. The well plugging priority criteria are likely different across oil and gas producing states. It's fairly clear that there's not one technology that will work everywhere. And we will need to implement a cost-effective scaling of existing state-of-the-art technologies because of the cost incurred, and we want to maximize the return of on our investments. So what I'll do is I'll show you some of the state-of-the-art technology that we're currently using and could be made available to stakeholders to characterize oil and gas wells after they are found. I'll start with a machine learning approach, followed by technology currently in use at increasing spatial scale and increasing associated deployment costs. So that slide could be the introduction slide, but also a slide that you can use as a concluding slide when we're finished. So next, so first, one interesting approach that we want to use to characterize and document well is data mining, fusion, and machine learning approaches. There are few databases, right? In California, for instance, databases provided by Dogger that has extracted information on metadata from well logs that can be directly mined. In other cases, a well record may have been run through optical character recognition software to extract text metadata. So this information from existing well or other well log information, and I'm showing some example here for geophysical logs that can be used to train natural language processing or image recognition machine learning methods to not only identify potential location, where many wells may be located, but also provide physical characteristic of the wells, like diameter of the tube, casing, how deep is the well, the type of well that we're dealing with, is cement present around the pipe, inside the pipe is well already plugged, and so on. And all those information could be, mined automatically. And as Kurt mentioned, that's something that could be very, very beneficial to stakeholders and states, in particular in Pennsylvania, because there's so much record that could be mined automatically. So it's worth noting that there's quite a bit of historical data also that can be processed through the same character and image recognition algorithm, right? So we could get a big, big database. I mean, the vehicle to collect all that information is in development, but also where do we put all those data is something we need to think about for the future databases that could be used by all stakeholders. Another technique that we use for characterization and that I would like to present is a borehole characterization tool that LBNL is developing with one of our colleagues, Yushen Wu. The principle is based on guided electromagnetic wave behavior in the megahertz to gigahertz range. It's a non-invasive method, meaning that it does not require work over rigs or downhole sensor deployment, which is very, very nice. It's intended as a quick screening tool to identify borehole damage. It is fast, with a simple survey setup and completion done in minutes. I mean, it has a lot of potential. Just want to give one caveat though. We have one proof of principle and a limited number of pilot tests that we have completed. But we believe that this project offers a unique opportunity to test this electromagnetic time domain reflectometry over a large number of deployment conditions. And I think we're again looking at test sites where we're going to test that technology, and also interested parties that would work with us on this testing. Another technology that we've talked quite a bit, another method in the past few talks used to characterize methane emission from oil and gas well is the flux chamber measurement method, which could be done in static or dynamic mode. Here I'm showing flux chamber measurements made in static mode with improvement we've done to the generic methods to assess larger ground areas and accommodate the nation variety of oil and gas wells that we might encounter. So this method uses a static flux chamber to measure the flow rate of methane coming out of a given well, as shown as in the picture in the upper left of the slide. What is a static chamber, right? It's a closed chamber that encompasses the footprint of the potential leak, which is sealed to the surrounding environment. And when coupled with highly sensitive methane sensor, for instance, that's where the cost comes in, you could use, and again, I'm not endorsing, I'm just saying that's one of the tools that we've used. For instance, a Picaro cavity ring down spectrometer for methane concentration measurements with a minimum detection limit for static chamber of 1 milligram per hour, so super sensitive. And then a linear increase of the methane concentration over time in the node chambers allows the calculation of the leak rate. And the leak rate can be represented by the relationship that I'm putting here, where Q is the leak rate in liter per hour, DC is the change in methane concentration in ppm over time period dt, V is the volume of the chamber in liter, and then you can convert to mass flow units in gram of methane per hour using measured air temperature and pressure in the chamber. So this method, although fairly low tech, besides the gas analyzer, requires approximately 1 hour per well, but is extremely sensitive. So again, when we keep this in mind, if we want to scale this to, let's say, okay, milligram, 500,000 wells, that's a lot of man hours. So that's one of also the challenge that we have. Another technique that we've developed here to characterize methane emission from the oil and gas well is mobile survey, which could be performed using a vehicle if access roads are available. So here I'm showing one implementation of the mobile survey method that we use. It's called the mobile plume detector, short MPI, developed at Berkeley Lab, which provide continuous roadway measurements of the vertical distribution of methane plumes, horizontal winds, and other meteorological variables needed to estimate methane emission from localized plumes. Right, the basic concept of the MPI is shown by the diagram on the left. of the slides, vehicle is driven through methane plume, continuously drawing airstream, in this case, from 12 inlets spaced about 0.30 centimeters along a 4-meter mast and aggregated into 3 streams, capturing 3 heights interval at roughly 0.5 meter to 1.5 meters, 1.8 meters to 2.7 meters, and 3 to 4 meters above the road. And air from those 3 streams is then continuously measured by 3 separate gas analyzers, each operated at a low flow of 250 standard cubic centimeters, and that acquisition rate sufficient to provide approximately a 2-second time response. And we also log the vehicle location, speed, heading data with a GPS, and we measure wind velocity with a sonic anemometer, and all the data is synchronized at about 1 hertz on a logger. So the benefit of this method is it allows for rapid assessment of methane emissions. It requires about 10 minutes per well, but is less sensitive than the static chamber method. Right? The next one I'm going to mention is based on airborne measurements that could be conducted from manned and unmanned platform. So there was a lot of chatter in the question about airborne measurements. So I'm going to first talk about the underlying methods that we use for this, which is based on mass balance technique. So the mass balance technique measurements is where an instrumented airborne platform records methane concentration as it flies through a methane plume. Flight patterns and local meteorology are combined with the data to determine an emission rate and location. The mass balance is attractive, approach is attractive, right, in its ability to identify local small leaks without require access. And I mean, those measurements, those techniques, inform much of the early understanding of methane emission from the oil and gas sectors that we've seen in the last few years. Of course, the downside of this approach stems from the fact that manned aircraft must pass through the emission plumes, requiring low altitude flights as well as the right meteorological condition to loft the plume, right? So that's a big challenge. Leak location at the sub-pad level is, to me, impractical with a manned aircraft, and that's where the unmanned aerial system that we've talked about, that Brian talked about, also come into play, using the same approach but with low elevation above the surface, right? So that's one of the key advantages. So since there was a question, and I'm glad I put my slide back on this, on airborne, so I want to spend maybe too much time on this, but we'll see. Lastly, I want to talk to you about spaceborne methane monitoring, which is a really active and growing field. There is an increasing abundance of direct measurements of methane using imaging spectrometer satellites, such as GOSAT, GOSAT-2, TROPOMI, and SKIAMAKI. We pave the way to satellite remote sensing of methane. But in general, this satellite provides too coarse a picture for monitoring individual wells. TROPOMI, for instance, provides column atmospheric methane measurements with a 7 kilometer by 7 kilometer spatial resolution, but near daily global coverage with its large 2,600 kilometer wide swath. This is well suited for understanding regional methane emissions, but clearly poorly suited for resolving a 10 meter by 10 meter well pad. Near-term follow-on, to those satellite GOSAT, to GOSAT and TROPOMI satellites, as well as the new CO2-M and Merlin satellite, will offer further enhancements, but not well at the scale of the pad. To me, where the picture starts to get very interesting for leak detection is with a handful of private sector missions that we've seen a lot lately. For instance, in 2016, a privately funded satellite, GHGSat, was launched with the purpose of monitoring methane emission from space. The imaging spectrometer aboard the satellite measures backscattered solar radiation with a high spectral resolution, with a spatial resolution of 50 meters by 50 meters in a 12 by 12 kilometer region. So, I mean, it's getting better and better, right? And observing the world from space has obvious advantage for identifying global emissions, irrespective of borders. However, there are also downsides to observing sources from several hundred kilometers away, right? First, still, the sensitivity of these systems is much poorer than aircraft and ground system, which limits them to detecting only large and super emitters. I mean, as we've seen with the recent study by Thomas Levaux, where they were able to detect globally ultra emitters from space, which was very, very nice, but it's for ultra emitters. And ultra emitters being, I mean, on our talks, we were talking about how many grams of methane can we detect. The ultra emitters are 2,500 kilos per hour. So that's we're talking about big sources. Second, satellite provide a single snapshot in time and long delays between overpasses, making it hard to locate intermittent sources, for instance. And the problem is worsened by the fact that the imaging spectrometer require clear sky and maybe frequently blocked by cloud in certain part of the world or the region of interest that we would be studying. On the plus side, there seems to be some commercial appetite for deploying constellations of these satellites, which should relax the visiting time concern, and the ability to forward land imager data will further help in this regard. So exciting progress being made. So the next slide that I want to briefly present to you the project team that we have assembled for well characterization that include experts from a consortium of national lab. So from the Berkeley lab, we have myself, Charu Vajaran, who is a machine learning expert. Yushin Wu is the EM TDR local expert. From the NETL, you heard from Natalie, and there's also Alexandra Hakala. From Lawrence Livermore, of course, you just heard from Brian Weil, and from the Los Alamos National Lab, there's Bhavendra Dubey also, and many more will join the team as we make progress. And I'm really excited about what we've talked about today, because I see so many more opportunities to collaborate with colleagues. And my last slide will be what we would consider as a success for us. It would be to establish best practices on well characterization. And I think because there's so much effort across different agencies and different labs, it'd be nice to establish best practices, working also with EPA, right? With also changing, having evolving methods to characterize methane emission from the oil and gas sector. So that would be a really good collaboration as well. And it'd be nice if we would improve methane emission estimate from undocumented, documented orphan wells. And I like the pre-post plugging approach, which also, give a lot of weight to the program, because we are also going to reduce methane emissions and potentially avoid methane emissions from wells that have, for wells that have their integrity in question, right? From using some of the techniques that we have. And then our goal is also to provide easy to deploy, cost-effective measurement technique for well characterization. And I think if we manage to do those three, that'll be a great success for the program. Thank you for your attention, and I'm standing by for questions.
Thanks, Sebastian. It was really interesting. So we have a few questions. So is the leak path usually predictable and confined to the wellhead casing or the immediate surrounding earth, or do we have evidence that it actually can escape from the small flux chambers you were showing?
So when we do surveys, we most of the time find the emission confined around the well. And as you saw in some of the pictures that I have, when the source point is more diffuse, we have much bigger, and if I can go back to my slide, much bigger footprint of the chambers that we have designed. So for instance, in one of the cases on that slide that I showed, I'm tempted to go back, but I don't know if I want to. Okay, let's try this. One more. So on the, do you see my mouse? No. So on the colorful pictures D, what we did is we sensed methane coming out of the ground, but that was a buried well. So we started to put, to dig to see if we were able to find the well, and the well was buried about 5 meters below the ground, and then we were able to really characterize that well particular. But from the surface, I mean, there was a fairly large diffusion pathway through the soil that was not, just a point source.
Thanks. So is subsurface characterization included in what we're calling characterization? Um, Subsurface characterization is important as the one at the surface. Undocumented orphan wells might cause more problems than just methane leakage to the atmosphere. In addition, if we plan to repurpose these wells, subsurface characterization is essential to determine the status of the well for future purposes.
Absolutely agreed. I wanted to add a slide on groundwater contamination, because that's also one part of the characterization we have, but I ran out of time to do this. But so we also, and that's an important environmental impact that we have. Also, I agree with you. The EM TDR technique that we use are going to really look at the integrity of the well to see if it can be used and repurposed, for instance, for carbon capture, right? For instance, you could imagine doing this. I think we will have characterization of the subsurface in terms of the geological features that are probably important as well. But I think some of it might be already available for some of the oil fields. So we'll see.
Perfect. And so I think a final question is, are we going to be putting effort into developing proper plugging technologies as part of characterization?
So that's not in our purview. My understanding is the plugging is not something that's in the program that we have.
Right.
So I would say, I'm sure somebody at DOE is going to look at different techniques to plug wells, but that's not something we will do.
Yes, I would agree. Thanks. Okay, well, thanks, Sebastian. I think we can now, thanks, and thanks everyone for continuing to ask a good number of questions. It definitely adds to the energy of the workshop. And so this is talk by Chet Weiss is actually trying to define what we think the outcome of our program should be. So please chime in, because we want guidance from all of you, because ultimately what we're trying to develop is for the states to use if we're successful. And so he's going to give a talk on the outcomes, and he's at Sandia National Labs. So thank you.
Great. So, hi, my name is Chester Weiss. I'm at Sandia National Laboratories. I'm in the geophysics department, and the research that we've been doing here at Sandia that pertains to this program has been around the characterization of wellbore casings and the surrounding geology using geophysical techniques, specifically electromagnetic techniques. This idea of wellbore integrity assessment is getting increasing popularity in the both, I think, popular scientific literature as well as the peer-reviewed scientific literature. And you can find recent examples of special issues of geophysical journals that are devoted entirely to some of these geophysical techniques. And so I think with that, we'll move on to how we are starting to think about what the possible outcomes of the laboratory consortium are going to look like. And I'll throw these out really just as a, oops, do I have control? There we go. I'll throw these out just as as straw man examples of what we propose to do at or what we're poised to do at the national laboratories. But really, these are just talking points for the start of what I hope is a much deeper discussion around what you, the states and stakeholders, would like to see from the national laboratories as part of our effort. Brief outline of what I'll be talking about is shown here. You were motivated by this idea of this is a problem of scale. We've seen some numbers posted earlier in the day about the number of undocumented wells that are out there. We've also seen the budgetary constraints, and what I'll argue is that the ongoing trope of smaller, faster, cheaper that motivates a lot of technology development today doesn't even really come close to addressing the scope or the scale of the need to address this problem in the 10-year time frame that the BIL funding is available. And so the approach that we are attracted to is what we're calling a wideband usability spectrum to maximize workforce engagement. And that is, we want we think that in order to identify and sufficiently characterize these wells, that it's a problem much larger than even the assemblage of states can put together right now with the BIL funding, and that there will need to be expertise that comes from kind of non-traditional elements of the workforce, namely citizen scientists, kind of trained geotechnicians, as well as specialists that that can help with the thorniest problems out there in this identification and characterization problem. And so from that from that perspective of trying to get as many people getting their eyes and hands on the problem as we can, we're looking at things like crowdsourcing or the identification and characterization effort. We want at the wellhead assessments that are as easy to use as some of the technologies that we see utility workers, marching up and down our sidewalks of our streets, looking for pipes and cables and so on. We want, fast, rapid, cheap stuff that doesn't require an excess amount of training to operate or understand. Of course, we're interested in standoff detection and characterization. This can take the form of drones or unmanned aerial systems, recognizing that there will be operational constraints that will vary widely across the nation because of existing laws about how drones can be used, about different vegetative environments, and so on. We also think that there are some opportunities in harvesting the existing database or the existing resources in newspaper clippings and maps and reports and so on, existing GIS databases. And these can all be kind of mashed up into this general effort around machine learning. One of the outcomes could be natural language processing, a method that can automate the aggregation of these different data streams. And then I think for the very hardest problems that are out there, we offer advanced data reduction techniques, so 3D modeling, multiphysics, and so on, as well as sort of specialized measurement discrimination techniques. And so with this kind of broadband approach, we're really trying to span the spectrum of both highly trained individuals to sufficiently trained individuals to just citizen scientist types. I think wrapping all of these different data streams up is a comprehensive risk assessment model that we don't think is, we don't intend to supersede the prioritization frameworks that the different states or agencies may have, but rather it's to inform how prioritization can be understood. And by informing prioritization, it means that we're looking at, what are the economics of the best, the best bang for the buck in terms of the different measurements that can be made. What is the minimum information that's necessary to make a prioritization decision? As we roll out these different technology visions through the laboratory consortium, how does the time frame of that rollout inform the prioritization calculation, and so on? And then lastly, we recognize that in the outcomes that there are going to be real challenges to the realization of these ideas. There obviously are going to be technical challenges. There are some things that we know how to do really, that we've kind of proven, proof of concept, but they're a long way from commercialization. There are other things that are a little more mature and a little closer to that commercialization end game. And so there's this idea of a technical readiness level that we'll be, I think, constantly revisiting through each of the options that we outline here. And not to be underestimated are the challenges of actually doing the handoff to industry. I think the intent of the program is not to have the national laboratories be the middle person in doing the identification and characterization assessments, but rather we are building the technology and handing it off, and in fact kind of commoditizing it commoditizing it in a way that we're no longer kind of the critical link in doing the the bulk of the data analysis. And so this means teaming with industry. How do we handle intellectual property issues? If we're talking about kind of cloud-based resources, there's database hosting issues that deal with maintenance and updates, points of contact. This is a 10-year program. And so, thinking about the continuity of expertise and responsibility is something that needs to be addressed early on. Indemnity is another issue that needs to be addressed early on, as well as our access, your access to lab specialists. And then again, hammering home this idea that because of the scale of the problem, workforce engagement is going to be paramount. We keep that in mind as well. So before we get into some of these details, though, I want to say thank you for everyone who responded to the survey that we sent out. We had 37 respondents representing 30 of the states. A couple highlights from this survey are shown here. One of the things that caught our attention was that the orphan and abandoned wells effort was rated as either a low or moderate priority by over 70% of the respondents. And so what I think this means is that you've got a lot of other things on your mind, and that this is going to be a problem not only of scale, but of constrained resources. So it further emphasizes this need for kind of, really kind of a revolution in how we think about workforce engagement and scalability of the problem. Because you have these other things that you're responsible for as the in your state. What we found in the state of practice presently is that a lot of the identification data that you presently use for finding these wells comes from these historical records, comes from landowner complaints, and from field inspections. These are non-technical data streams. And so further emphasizes, I think, our sense that things like natural language processing or kind of, integrating these existing analog data streams is something that could be quite useful to you. In terms of the data gaps that you see within your state, finding these wells tops the list, of course, but also well construction and mechanical integrity. In other words, what is the well made of and how stable is it? Is it, is it a good candidate for plug and abandon, or is there other work that has to be done? Are there potential leakage pathways of methane or other contaminants into the atmosphere and the groundwater supply and so on? One of the things, though, that these responses highlighted for us, though, is that whereas the states identify location and the wellbore integrity as and wellbore construction as primary concerns, the legislative priority is methane emissions. And so that is something that will largely be driving, how we think about these the different technologies and how we define the success metrics for the technologies. So the state of practice is largely intensive. There is labor intensive. It's largely non-technical. You want to know where it is, what's the state of health, and that elsewhere in the survey we saw a lot of evidence of varying local constraints on doing the identification and characterization problem. For example, in Idaho, you're legislatively prohibited from doing drone surveys over private property. Finding other ways to do standoff assessments are definitely, I think, things that we need to consider. Further emphasizing this, and briefly emphasizing this point of, smaller, faster, cheaper. We've seen estimates of like 300,000 to 800,000 undocumented orphaned wells. There are other reports out there that say there's up to 2 million or so of these unplugged and abandoned wells in the U.S. With the $4.7 billion available, although that seems like a large amount of money, it means that you're looking at a couple of thousand to a few tens of thousands of dollars per well. And that story isn't going to change much as these numbers get refined, get further refined. And so it also means that you're looking at something like 20,000 to upwards of 100,000 or so wells per year over your 10-year lifetime that the BIL money is accessible to you. And to put those numbers in perspective, the state of practice is, on the order of like 50 wells per year, for a given area of responsibility. And you can talk to, service providers as well, and they say, look, if we were to deploy all of our crews, and dedicate them entirely to this P&A effort, that's kind of where they're standing in terms of how many wells they can turn around in a given year. And as pointed out by, I think it was the state of New Mexico, a lot of the cost of and time in doing the P&A operations is actually in the mobilization and the demobilization part of the P&A operation, rather than the actual on-site P&A operations themselves. And so, we see these numbers, these crude estimates of what the or these kind of back of the envelope estimates of the the scale of the problem that's in front of us. And we see that we need to upscale our current decisioning factor by something 40 to 400 times to fully meet the expected needs of the anticipated inventory of orphaned and abandoned wells. So this is more than just faster, lighter, cheaper. This is something altogether new. And so our straw man strategy is this. It's this wideband usability spectrum where we engage people at every level of technical training or expertise, from the every person citizen scientist with a smartphone on one end of the spectrum to the highly skilled and focused PhDs like we have here at the national laboratories who are adept at the 3D modeling, integrated analysis, these kind of more specialized measurement discrimination technologies. But then in the middle, we have the geotechnician, the person in the hard hat in the truck who's going out to the wellhead, who needs something quick and easy to make a go, no-go decision about whether further assessment is needed or whether enough is known about the well to greenlight a P&A operation. And so there are we have this concept of, kind of a portable, easy to use commodity technology, similar to these utility detection systems that we see used all over urban areas. The offset assessment areas, again, I think are in the realm of the kind of technically trained. And here we're looking at, the full spectrum of spatial resolution, from satellite to airborne to drone, and recognizing that these are all in different states of maturation and usability, but the idea of a hierarchical approach to focusing our attention on problem areas seems to be a sensible way to go. And then lastly, as I mentioned before, this natural language processing and the GIS data fusion for archival analysis is a way to upscale the analysis and usability of all of the archival data that the states are presently using right now. So going through these one by one, the smartphone data collects. We have some experience in this. In fact, DOE has funded software development efforts for well locations for abandoned water or for water wells. We think that this is an absolutely outstanding way to engage kind of the citizen scientist because it's easily accessible. And we can also augment these web phone apps with the new sensor technology that's embedded in our smartphones. For example, the iPhone 13, the Pro version, I think Pro Max version as well, is equipped with a LiDAR system, a LiDAR camera in it. And cell phones have long had magnetometers in them. And there's been a growing amount of geophysical research about how these cell phones can be used as cheap and widely deployable geophysical sensor platforms. And so we think that doing something like what was done with the water well identification problem, but expanding it to the orphan and abandoned well problem, where we complement not just the pins on a map, or we complement the pins on a map with kind of crude geophysical data that comes from the cell phone itself. And this can give us a rough cut of how to prioritize these newly discovered wells. It expands the workforce and is, I think, an intriguing opportunity for public engagement as well as outreach and education about what the labs do, what the DOE does, how we serve the nation, and the importance of these greenhouse gases to our collective future. For the technically trained, this is the paradigm that we're working with. We want the geophysical analog of utility detection, kind of an all-in-one sensor package that I think is going to be more than just the metal detector that you see here, but something that may have a magnetometer, an EM sensor, maybe a methane sensor attached to it. We can envision options where there's onboard data analysis and geophysical interpretation that happens on the chip. And we also see that there are opportunities for these devices to stream their data, upload their data to central servers, where the data can be then archived and QA'd, but also gets access to different machine learning and cloud algorithms, which then communicate back to the device itself that can tell the worker, go here, go there, repeat this measurement, and so on. So sort of an Internet of Things approach to the wellhead characterization. Something similar to when your iPhone, mysteriously pops up a message saying, you appear to be close to a Starbucks, even though you never told it was that you were going to a Starbucks. Our standoff options are, we've seen lots of examples of these standoff options. The national laboratories have a significant investment in not only developing these drone and unmanned aerial systems. We can build them, we can optimize them for weight and power, and flight duration, as well as different types of sensor packages. We have expertise, or we have experience flying these systems in different parts of the country, which I think represent some of the challenges that we'll face in the orphan and abandoned wells problems. So sensitive areas, ecologically sensitive areas, populated areas, places where there are restricted flight rules, and so on. Here are a couple of examples of the stuff that we have that we've built here at Sandia. Livermore has, as you've seen similar other examples in the talk earlier talk today. But these are the sorts of things that are on the table for us in terms of building these integrated autonomous systems for standoff evaluation. And again, I think this is something that is kind of at the skilled technician level, certainly not the citizen scientist, and I'm not sure that that it's something that we want to pigeonhole into the specialist, the realm of the specialist operator either. So yeah, with that. Let's see, for the technically trained also, we see natural language processing as a way to deal with this archival data. And so just to make sure we understand what we're talking about here, it's about programming computers to understand and analyze large amounts of natural language data. So handwritten, typewritten, or typeset documents to kind of understand content and the nuances within. We've been reminded that oil and gas exploration has been happening in North America for 160 years, and that means there's a wide variability in the technology used to record these operations. And so with these various historical documents, whether they're newspapers or maps or reports or so on, the first step is an optical character recognition algorithm, which is no trivial task, especially with some of these archival documents. It can be quite challenging to figure out what is actually present in those paper documents. But once it's been digitized and once these images have been translated into letters and numbers, then we have access to machine learning algorithms, which are really the modern natural language processing approach. Natural language processing is something that's been around for a long time, and people have tried different semantic correlation techniques and so on. But machine learning is really the new frontier in NLP research, and the labs have made significant investments in this technical area. And what you get out of this then is a likelihood estimate of where these undocumented well locations are. And so this directly points to the identification problem. But there are lots of steps that you can see here. And so, open questions that we need to address in at the labs here and with your input is, what is the best interactivity model between you, the users, and a natural language processing algorithm? Are these standalone algorithms? Are these cloud solutions? What sort of human capital are we looking at in terms of making this effective at scale? These are all questions that I think will kind of scope out what the options are for going further in this direction. Also digging into the archives, we have just loads of various data, both historical records as well as more modern digital records, which lend themselves easily to geospatial analysis, maybe ultimately machine learning analysis. What this can do then is, I think, produce a data product very similar to what the natural language processing promises. And that is, by correlating these different data streams through, our algorithms of choice, we can then focus our attention on areas of high likelihood of undocumented wells. For the advanced characterization and measurements, we think that this is something that is maybe well suited for the specialist, and some of the technologies that we've some of the technologies that we've seen earlier today at the laboratory. There's at the different laboratories, there are a lot of ways for a well bore to fail. It's not just about broken casing. There can be delamination between the outer casing and the cement. You can have compromised plug seals. You can have unwanted excess cement porosity, broken casing, fractured cement, delamination between the cement and formation. These are all potential problems when thinking about the potential for methane emission into the atmosphere from the subsurface, as well as contaminant migration from the wellbore to the surrounding geology, as well as potentially contaminating, adjacent geologies within the subsurface that were not the initial exploration or production target for the well itself. So we have a number of candidate characterization methods. Sebastian talked about time domain reflectometry in the previous talk. That's one of the hot new topics that we're poised to pursue, both in an acoustic sense and electromagnetic sense. This would involve excitation of the wellhead using either an electromagnetic or seismic source. We have different types of surface-based measurements that allow us to infer the geology and the geometry of a wellbore, as well as potential fluid migration pathways adjacent to the borehole, all from surface-based measurements. These two are kind of cutting-edge ideas that are at a relatively low technology kind of readiness level, but things I think would be really valuable to augment some of these more rapid turnaround ideas that we just discussed. And then I think wrapping this whole thing up, I mean, this is, there's a decision maker that's going to be part of the equation here. And so the labs have extensive experience in these kind of systems level approaches to understanding problems where, we take our expertise in subsurface flow modeling, in power grid in understanding power grid requirements and so on, and integrate these different and kind of disparate physics and kind of demand structures into an integrated model where we can start asking questions, answering questions about larger kind of system level drivers that may affect the overall system, and also answer questions about what are the particular sensitivities from a systems level approach. And so if we we've done this with water and power, for example, here at Sandia, but I see that within this program, that if we were to couple the plug and abandon activities with factors like workforce availability, the timeline of tech development, the potential footprint of what that tech deployment looks like, other ecological factors like groundwater impact, how this ties into methane mitigation goals from a legislative point of view, how these plug and abandon activities are countered by the effects of actually doing the plugging and abandoning. For example, using cement to plug and abandon these wells results in the production of CO2, which comes out to on the order of 6 tons per CO2 per kilometer of plugging. And so if you've got 1 million wells that you're dealing with at an average depth of 1 kilometer, you're now looking at 6 megatons of CO2 just to plug and abandon the inventory, which I think is a number that merits some attention. We have ecosystem and societal impacts that play into the systems level approach, as well as kind of an evolving set of external drivers like such as economic drivers, population change, climate projections, repurposing options such as carbon capture options, repurposing for scientific operations or geothermal operations like we saw in the case of Arizona. All of these kind of levels of interactivity between the P&A operation and everything else it touches is something that I think is largely unexplored and merits some attention so that we can make the best decisions we can about how to focus our attention and the technologies that that we bring to bear. And so, in short, it informs our prioritization options and risks with what measurements to take and when, and how do we return our maximize our return on investment. The challenges to realization, as I talked about earlier, are kind of threefold. There's the advancing technology readiness levels. Here at the labs, we work with a, there we go. We work with a kind of a standard scale of technology readiness shown by the thermometer on the right here, where we elevate ideas from kind of basic technology and research all the way through a demonstration phase to an operational phase at the top. And so each of these is well defined. We have a rigid structure through a rigid structure of gateways through which we pass to go from the different TRLs. And so this is something that anything that we propose, whether it's the smartphone or the optical character recognition or the natural language processing or whatever, we'll go through this kind of formalized TRL sequence. And so that's the first challenge, is just marching our way through the TRLs. The second major challenge is the handoff itself. So it's dealing with industry and all the related details that involves, such as intellectual property, indemnity, who's going to be, there's kind of a continuity of conversation and responsibility for the technologies, since this is anticipated to be a 10-year program, maintenance and updates and so on. This is I think a non-trivial part of the technology space that we need to I think get our hands around earlier rather than later. And then lastly, and I should say that, you know, we do have some experience in this through in teaming with industry through cooperative research and development agreements. It's a formalized way for the labs to team with industrial partners. And the laboratories also offer post-development licensing of intellectual property, which can be at low to no cost models to minimize barriers to adoption. And so this isn't territory that this is territory that we're familiar with, and mechanisms are in place to expedite it. And then lastly, again, because of the scale of the problem, we see broad spectrum workforce engagement as being really critical to making a meaningful dent in just the size of the problem in front of us. This citizen science, this concept of the citizen science is something that's gotten a lot of attention in the science, in the peer-reviewed science literature. We see all sorts of papers now coming out about, you know, in all aspects of kind of the physical and observational scientists, where technologies that get deployed on cell phones or even, you know, lower tech options are put in the hands of novice users, and they create significant contributions to our knowledge. And so I think there's opportunities here for that with this program, and it merits our further attention. And so with that, I'll take questions, and thanks for your attention.
Okay, thank you, Chet. Nice to wrap it all up and with the outcomes. So we have a few questions. Is there a plan to develop standardized tagging or providing minimal monitoring of undocumented orphan wells that have been found, so that we can ensure that they're easily found again for plugging later?
Is there a plan? No, as I said, these are all, so I won't speak to what other states have done. Maybe, I think Natalie in Pennsylvania probably have the greatest experience, in the state of Pennsylvania have the greatest experience with this. But that is certainly, you know, anything we do to kind of, you know, minimize redundancies is of effort is something that we'll want to make sure happens. But, you know, as I said, you know, these are kind of what we have our concepts here around how we see the accessibility and usability of the technology solutions to the broad spectrum workforce. And so, you know, the details of what this will look like are, you know, it's yet to be determined. But I think that, you know, hitting these different components of the workforce is kind of the binding structure around where we, you know, how we see our efforts here at the lab.
I mean, I would say that, yeah, we should definitely have a plan for tagging things that are found, and, you know, figuring, you know, because I think that's, you know, the minimum that we could do. Would it be beneficial to set up a system like what the USGS has for monitoring earthquakes, where citizens can report whether they felt it or not, kind of like your citizen science? This would be geared more towards if you're out for a hike in the woods or hunting or find a pipe on the surface, have the person report it and have the AI cross-reference with known wells to identify possible undocumented wells.
Oh, sure. I mean, this opens a whole, you know, a whole spectrum of different ways that we can, you know, how the data is archived, how the data is analyzed, what the different data products are from the, you know, from the citizen scientists. It's, you know, one of the good things I think about that, the USGS's earthquake program, is that it's not just a one-way street. It's not just the citizens saying, hey, I felt this type of activity near my home or on my way to work. But then people can log into the site and they can then learn something about, you know, what the earthquake was, where it was located, how big it was, you know, how many people it affected. And so it's a give and take, where the citizen scientist provides something and then they get some sort of, you know, analysis or data product in return. I think that's something that kind of needs to be part of the equation to, you know, to make sure that we get this buy-in. Otherwise, it's just kind of a, it's an ask of the citizenry. We just keep asking and asking and asking, and maybe giving little in return. And so, part of that science feedback, I think would be a really enticing part of the of this vision.
So we'll do two more questions before we do the closing remarks, which will
Hmm.
be pretty quick. So has anyone come up with a set of parameters required to decide if a well can be repurposed? It's expensive to drill a well, so it seems like a shame to just cap it if it could actually be used for other things.
Yeah, so I think the options that that seem to be getting the most attention right now are we've seen options for geothermal reclamation or repurposing for geothermal operations, carbon capture operations, and then there's also a lot of these abandoned oil wells that are being re-instrumented for kind of regional seismic monitoring of not only earthquakes, but also other anthropogenic activities. And so those are kind of the big three opportunities I see for repurposing right now that are getting a lot of attention. But I think that the requirements for each of those different operations are wildly different. And since they're still largely in this kind of experimental phase, that as we move into more of a as they move into more of a production mode, we'll have a better understanding of what are the best what do we need to look for in terms of strong candidates for a particular repurposing option.
Okay, great. So we'll do one final question, and remember, we will document all these questions, so we will for the ones we can't get to. But just a thought. Is another choice to shortlist areas prior to the actual survey with incentive programs to shortlist undocumented wells across states by engaging the citizens to locate, report undocumented wells. Could be similar to Florida's Burmese python population elimination program.
Sure, yeah. I'd have to think hard about how the national labs could help that with that incentivization. But yeah, of course. I mean, it's got to be kind of a two-way street. It's in terms of what we ask and what we give.
Cool. Okay, well, thanks, Chet, and thanks everyone for hanging in there. We've had really good attendance and really good participation, so I really appreciate it. So we're just going to wrap up with Bill Carey from Los Alamos National Labs to just kind of give a summary of what you heard today and where we want to go from here. So thanks. Go ahead, Bill.
All right. Thank you, everybody, for participating and being here. I thought those were a great set of talks from everybody, from Department of Interior, Department of Energy, down to people like myself working at the national labs doing research on various esoteric aspects of